But we do want to talk about the process that occurs here as we go through different phase changes and heat things up, okay? So let's say we've asked the question a couple times. We asked in 105, and we also asked just the other day about how much energy does it take to convert, maybe 32 grams of water into steam, right? But what we haven't considered is how much energy does it take to convert, say, ice into steam. And in order to think about that, we have to think about what's going on. So we have to take the ice and we have to heat that ice up to its melting point. And that's going to take some energy to do, right? We got to put energy in to raise the temperature. You probably remember, or hopefully you remember from Gen Chem 1, that we have this equation Q is equal to MC delta T. Does that ring a bell? So M is the amount of stuff that you have, the mass. C is the heat capacity of that thing, and that heat capacity means how much energy does it take to raise the temperature of 1 gram of the substance 1 degree C, and then there's a change in temperature. And so we put in some heat, and we raise the temperature, and we get to the melting point of that ice, okay? Now, as we continue to add heat, we don't change the temperature, and that's what the first flat part on the graph is there. So the melting point of water or ice is 0. We get to 0, we see a flat part on the graph there. That flat part is me adding heat with the temperature not changing. And so what's going on there is that we're changing the state of the material. The heat that goes in breaks all the intermolecular forces and causes the solid ice to convert into liquid water. Right? And so that amount of energy there, that is the enthalpy of fusion or enthalpy of melting. Okay? So we got step 1, which is warming the ice, and step 1 would use Q equals MC delta T. Okay? Step 2 there, though, there's no temperature change, so I can't use Q equals MC delta T. So if I wanted to know the amount of energy here, what would I do? What would I have to use if I want to calculate the amount of energy in step 2 there? Say again? We need the enthalpy of fusion, that's right. So we need delta H, fusion. Those values are in units of kilojoules per mole. So if I know how much stuff I've got, then I just multiply by the number of moles of stuff. Okay. So then I've converted everything from ice into water. Well, now that I have water, I can add heat again, and the temperature should change. And so step 3 here is heating again, and this is going to be another Q equals MC delta T. The difference is that the C over here is the C for the solid, and the C over here is the C for the liquid. They have 2 different heat capacities because they're in different phases, right? Think about what that means. The molecules are in different places inside the sample, right? In the solid, you can see in the picture up there, they're in that hexagonal arrangement. In the liquid, they're bouncing all over the place, rolling around each other like ants in an anthill. So because of that structural difference of the molecules, the amount of energy it takes to heat it up changes. So we can use this Q equals MC delta T to go all the way up to the boiling point. Once we get to the boiling point, now we have a situation where we're going to add heat again, and the temperature is not going to change. Now we're adding heat, and we're overcoming all the intermolecular forces to turn a liquid into a gas, right, into a vapor. And so that's what we're seeing here. That big flat spot is the enthalpy of vaporization this time. So now we'll have delta H, vaporization. Once we convert everything into a gas, then we can heat the gas up with another Q equals MC delta T. This time it will be the heat capacity of the gas. Okay. So if we wanted to calculate how much energy would it take to convert 15 grams of ice at minus 25 degrees C into steam at 125 degrees C? It would be a 5-step process, right? We would make the solid heat up, then we convert the solid to liquid. We'd make the liquid heat up, we convert the liquid to a gas, and then we make the gas heat up. Can everybody follow the 5 steps here? The set points are different for different liquids or solids, right? It depends on the material. The melting point is going to be whatever the melting point is for that material. The boiling point is going to be whatever the boiling point is for that material. Okay? The delta H's will be different for each material, right? So the length of that number 2 and the length of that number 4 will vary with delta H. And then the points that we go to vary with the material as well.
So let's take a look at converting 1 mole of ice from minus 25 degrees C to 1 mole of steam at 125 degrees C. And so like we said before, this will be 5 different segments. The first segment is going to be the heating of the ice, and it follows the equation Q equals mc delta T, where C is the heat capacity of the solid ice, M is the mass of the ice, and T is going to be the temperature change. So if we take a look at our equation below, 1 mole of ice has a molar mass of 18 grams. If we look up, the heat capacity of ice is 2.09 joules per gram degree C. That's a specific heat capacity. And then our change in temperature, our delta T, we're going to go from minus 25 degrees C, and we're going to go to the melting point, which is 0 degrees C. When you calculate changes, it's always final minus initial. And so that's why you see 0 minus a negative 25. And so that delta T works out to be 25 degrees C. So now we have 18 grams times 2.09 joules per grams degree C times the change in temperature of 25 degrees C. And if we were to calculate this all the way through, we would get 941 joules. But heat is going to be typically reported in kilojoules. So if we make the conversion, we get 0.941 kilojoules.
Okay, so the next step, segment 2, is the actual melting of the ice once it reaches the melting point. So this is where we're going to add heat, and we're not going to see a temperature change. This is the flat part of the graph. And the amount of energy it takes to convert from solid to liquid is called the enthalpy of fusion. And that value is given in kilojoules per mole. So in order to determine the amount of heat that we need to convert from solid to liquid, we just need to take the number of moles that we have and multiply by the enthalpy of fusion, which is in kilojoules per mole. In this case, we're converting 1 mole of ice. So it's going to be 1 mole of ice multiplied by our enthalpy of fusion, which is a tabulated value of 6.02 kilojoules per mole, gives us a heat of 6.02 kilojoules. Okay, so our next segment is segment 3. This is the heating of the liquid water after everything has been converted from ice to water. So we're going to use a Q equals mc delta T equation again for the heating here. We still have 1 mole of water, so it's still 18 grams. Now we're going to need the specific heat capacity of water, which is 4.18 joules per gram degree C. And then we're going to need our temperature range in which we're working. And we're moving from the melting point, 0 degrees, to the boiling point, which is 100 degrees. So you can see our delta T is going to be 100 minus 0. So when we do the math, we're going to have 18 grams multiplied by 4.18 joules per gram degree C multiplied by 100 degrees C. And when you do the math here, we get 7.52 times 10 to the 3 joules, or 7.52 kilojoules. All right, our next segment is segment 4. This is the actual vaporization of the water. So we're turning it now from liquid into gas. This happens at 100 degrees C at the boiling point. And you can see that the flat part on the curve here is really big. That means that this has a really large enthalpy of vaporization. So again, we're going to be using the enthalpy of vaporization in order to calculate how much energy it takes for a phase transition. In this case, again, we're going from liquid to gas. We see such a large enthalpy of vaporization due to all the hydrogen bonding that's present in liquid water. So it's that structure again that determines what our enthalpy is, and those intermolecular forces that determines what our enthalpy is. So if we look up the enthalpy of vaporization for liquid water, we see it's 40.7 kilojoules per mole. And we're working with 1 mole of water, so this is a pretty straightforward calculation. 40.7 kilojoules per mole times 1 mole gives us a heat requirement of 40.7 kilojoules in order to convert this 1 mole of liquid water into steam. Okay, our last part of the curve here, segment 5, is another heating segment. We've actually turned everything now into the gas phase, but we just need to heat from the boiling point of 100 degrees up to our target temperature of 125. So because we're heating, it's going to be another Q equals MC delta T equation. We still have 1 mole of water, so that's 18 grams. We now need the heat capacity of our of our vapor. So we need to look up the heat capacity of our vapor, and that's a typo on the slide here. This should be C sub V or C sub G for vapor or gas, not the solid. So we take our 18 grams, we multiply by our heat capacity of the vapor, which is 2.01 joules per gram degree C. Our delta T is going to be, we started 100 degrees C at the boiling point, and we're increasing to 125. So our change, you can see again, is 125 minus 100, or 25 degrees C. So now do the math. 18 grams times 2.01 joules per gram degree C multiplied by 25 degrees C gives us 904 joules, or 0.904 kilojoules. So now if you want to know the total heat for the entire heating curve, from going from our ice at minus 25 to our steam at 125, all you have to do is go back and add the heats for segment 1, segment 2, segment 3, segment 4, and segment 5. Total up those 5 terms, and you'll have the overall heat for the process of going from ice at minus 25 to steam at 125 degrees C.